So let's consider a matrix for Gauss elimination algorithm demonstration. So I assume here a matrix to represent a linear system of equations ax equal to b of size n by n. So I have elements a11, a12, up to so on, and up to a1 and n. Okay. Then I have the entries 21, a22, and so on, a2n. And likewise, I have the last row for the squared matrix. It is an1, then an2, and so on up to a and n. In Gauss elimination method, we do the row operations. And the row operation is defined by considering the diagonal entry as a pivot entry. So with the help of this one, we define a row operation in such a way that we get 0 below the diagonal entry. So our effort will be to bring all these entries, for example, a21, a31, and all up to an1, all zeros, right? So for this one, we have to have n-1 operations, n-1 operations, all of similar type. For example, to bring a21 to 0, I require an operation like a21 is equal to the old value of a21 minus, I require an operation a21 divided by a11 multiplied by a11. So it is going to be defined with these two numbers. So right. So it is going to be defined like this. And the rest of the entries in the second row will be updated with this operation. And here is the multiplier. So you can see that with this multiplier, a21 will become 0. Similarly, for a31, the operation will be a31. That is our prime objective. a31 minus a31 divided by a11 times a11. So this is the multiplier. This is the multiplier. So in general, in order to bring all elements 0 below a11, we require an operation on all the rows. For example, if I select a kth row, so it will be, the operation will be rk minus the first row and with a multiplier, and multiplier is defined with the first entry a k1 divided by a11, right? So with this operation, all the entries below this first leading diagonal, they will become 0, right? And for one row, if I write for this problem, the RK row, if I write the elements of RK row, since Fortran and any other compiled language like C and C++, they are going to perform operations on element by element. So we should be able to identify the elements of kth row. So in a kth row, the first entry, first index will remain k. The second element would be AK2 and so on. So there will be AKN. And elements of first row will be A11, A12, and so on up to A1N. So in journal, if the operation is applied, that can be written on a journal entry. On a journal entry, if I identify a journal entry some Lth entry, right? So the operation will be the corresponding in the kth row, the Lth entry will be updated as from its old value AKL, kth row, Lth column, minus the row operation as it was defined AK1 divided by A11, because we are bringing, we're going to bring the entry below A110, and it is to be multiplied with the corresponding entry in the first row, which is A1 and L. And where this L varies from 1, which is to represent an entry below A11 in the kth row, and it goes up to N to apply the row operation on all the elements. So this is something actually we do for bringing all the elements 0 below A11. Then the structure of the matrix will be, we will have A11, A12 up to so on, first entry as it is, first row as it is, right? And by the way, while solving this thing, we have to correspondingly update the entries of B column vector, because we are solving the AX equal to B system. So the same operation on the Lth row, let me write that one on the previous page. So likewise, the kth entry of B vector, column vector, will be updated BK minus the multiplier as it is AK1 divided by A11 times B1. So this has to be applied on the column vector as well, the right hand side of linear system. And we will have then zeros with these operations, right? And then we have the updated values like A22 prime, A23 prime, and so on and so forth. And similarly, all the entries of the rows will be updated, because the row operations have been implemented. Now, our next task is to bring the zeros below the second pivot entry. Below this second pivot entry, we have to bring zeros. So this is the task. Now, the multiplier will be defined with the help of this diagonal entry, and our objective is to bring zeros below this one, right? So again, if I consider the operation on kth row, the operation will be RK minus the multiplier. So let me write here the entry A prime K2, right? This will be the entry to define the row operation. So the multiplier will be A prime K2 below the diagonal entry divided by A. Now the diagonal entry is A22 times R2. You can identify the elements of R2 and RK. So again, a similar operation like this one. And here you have the only difference of A11 to be replaced by A22. And the same way the operation is going to proceed, right? You can notice that there is no need to apply the operation. Earlier we applied this operation for all the elements in the row, right? But now at this stage, we have already zeros here. So we can save one innocent operation by multiplying zeros and adding zeros to zeros. So you can start operation here, like the L earlier defined from 1 to N. Here you can define it from 2 to n. Likewise, when you are at the stage of A33, let's get to that one, and I think that will be sufficient demonstration. If I write here, I have A11 undisturbed, A12, and so on up to A1n, and I have zeros below A11. I have A22 prime, A23 prime, and so on up to A2n prime. And below this one, I have made zeros. And then the entry is here, A33. Let me write it with the double prime, which means it has been updated twice. One with the row operation defined with the first row, and second time it was identified. It was changed with the second row operation. So it is this notation, right? And now we are to bring zeros below A33, right? So you can see the pattern. At first, we defined the operations below A11. So operations were defined for all the entries below here, right? So for example, you can say for row operations, and how many row operations are required? At first, we have to define the row operations from the first entry, then from second entry, from third entry, diagonal entry, and up to an entry here, n-1. So you have to define row operations n-1 with respect to n-1 diagonal entries, right? So row operations, if I say I would vary from 1 to n-1. Okay. These many times row operations on making below the diagonal entries zeros. In the first entry, to bring zeros, you have to apply row operation on n-1 rows. Next time, n-2 rows. Next time, n-3 rows. So every time the number of row operations are reduced, right? Okay. And then so how many entries you have to bring zeros? So I say, if I say j, so j varies from this one is A21, right? This number was A21, A31, A41. So this number is I plus 1, and it goes up to n. Amazing. And the third one, this is to define number of row operation, number of the diagonal entries that you would like to use in row operations, the number of elements you would like to make 0 below the diagonal, and then the third index that I demonstrated as L, it runs from, for every jth operation, it runs from j to L to n for defining the whole row, right? So these three indices, three loops are going to be recognized and implemented in the Gauss elimination algorithm. In the development of this algorithm, I have assumed that in the process of applying row operations, I do not encounter a zero entry at the diagonal. And if we get a zero entry at the diagonal one, we can do the row interchange operation. So before implementing any row operation, like the attempt to make zeros at below the diagonal entries, we apply a condition that if the diagonal entry is 0, we state a condition that if the diagonal entry, which is aii, if it is equal to 0, then we have to make a row interchange operation, right? So for that one, you will search for a non-zero entry at least. And from practical purposes, we look for the largest entry in that particular column and then bring that one to the diagonal entry, right? So that is the procedure that we have to implement in a systematic and intelligent way and in a careful way. And ultimately, it will bring our system to a simple system, which if I write in simple form, it is A11, A12 up to A1n, right? Then A22 up to 2n and up to so on. And this is going to be an upper triangular matrix where you have non-zero entries on the principal diagonal and also above the, well, not necessarily above the principal diagonal. You may have different situation, but necessarily all these zero entries below the principal diagonal one. And then you have the vector x with n unknown, x1, x2, up to so on, xn, and equals the updated and modified values of v1, v2, v3, and of course they are all modified in the process of implementation of the row operations. So that is the scheme of Gauss elimination method. On these lines, you can also implement the row operations above the diagonal to come up with the Gauss-Jordan elimination. So in that case, whatsoever we have learned, we implemented the row operations just below the diagonal. J started I plus 1 to n. So you can say apply this operation on all the elements excluding only the diagonal entry. So apply the row operation below the diagonal and above the diagonal. So you have the Gauss-Jordan algorithm program. But the Gauss-Jordan algorithm is numerically expensive as compared to Gauss elimination plus a back substitution program, in which we start the substituting the values of x in the reverse order to get to the next value of x in the previous equation. So like for completeness, from the last equation, we have this equation ANN xn is equal to bn. So we can eliminate xn here. Xn is equal to then bn divided by a and n. And then xn minus 1 will be equal to, from the previous equation, from the equation above line, we have the two unknowns, xn minus 1 and xn. Now we have the value of xn, so we can do the substitution. So we can say xn minus 1 will be equal to the corresponding b value, bn minus 1 divided by, minus a n minus 1 n multiplied by xn and whole divided by a n minus 1 n minus 1. So this is basically a rearrangement of the second last equation. So and there is the indices can be understood if you have gone through the matrix multiplication algorithm. So these are straightforward, and we can write in journal some equation. For example, if I write quickly for the kth one, so it will come from bk, right? So all the values of x after xk are known at this stage. So xk plus 1, xk plus 2, up to xn, they are all known. So they will be written in a summation like a aj xj, where j is comprised of all the entries which have index above k plus 1. So I can write k plus 1 up to n and divided by the diagonal entry with the xk, which was a kk, right? So if you can identify the elements of a matrix, then this is pretty straightforward. So with this demonstration, I hope you can confidently work on the Gauss elimination and back substitution algorithms. They really form the backbone in the direct methods of solving a linear system of equations.